Welcome back, everyone. In this video, what we're going to take a look at is the export directory, or exports in typically DLL files or library files, but executables can export functionality as well. The main reason that we're going to do this is because I'm going to have a couple of videos here in the near future that will walk you through code that does this, shell code and malware, anything that either needs to resolve its imports dynamically or chooses to resolve those dynamically, essentially as a form of obfuscation. Okay, so going to get a little deep into the weeds here, get a little technical, probably get a little lengthy. If you haven't watched some of the previous videos on the import structure or PE files in general, I have a playlist available, so I'd encourage you to go and check that out before jumping into this content here. But again, this will be important content as we'll cover it later on. Now, there's a couple of pretty good references actually on Microsoft. I'll get these links posted in the description. The first one just provides you with a broad overview, talking about some of the major parts of a PE file. It's actually quite dated, but I'm not super familiar with kind of the evolution of the PE file, but it doesn't look to have changed drastically over the years. The second is another article actually on MSDN or on Microsofts.com. And this has a lot more detailed information about the PE file format, the structures, and even the members. So again, I would encourage you to maybe bookmark this or grab this link. Just have it handy as we're going through this content together. Now, to try to keep things short, I'm going to jump right into the export directory. One of the main reasons I wanted to share this, other than just being a good reference, is that it has a pretty nice diagram about the export directory, the image export directory, as you see here. There are some fields that we're not going to care too much about. The main ones will be the number of functions, the number of names. That allows us or anyone who wants to walk an export table from a library to know how many functions are there. And you'll see that done in sort of an iterative fashion. Let's say particularly that there's some code that's walking an export directory looking for a specific function. Well, with this number of functions, number of names, it knows then how many times it can iterate basically through that export table before it runs out of, before the loop should terminate. There'll be three other structures then. Address of functions, address of names, address of name ordinals. And we're going to go through these sequentially. As you can see here, these are essentially pointers to typically an array of RVAs, relative virtual addresses, that represent some important aspect of identifying or finding those exports. So the address of name, as that name suggests, that's going to be an array of RVAs that point to, when we add those RVAs to the image base, the actual name of the function. The address of name ordinals is going to be an ordinal value, and that also will be an array of RVAs that then contain the ordinal value. The ordinal value is used to index into the address of functions, and then that will be an array of RVAs that we add to the image base to get the actual function from that library. So in order to index into this address of functions, we're going to actually get the address of name ordinal value in order to know what index to look here. How do we know what value to get out of this address of name ordinals? Well, if we're just iterating through our address of names one by one, we can increment a zero-based counter, and whenever we find our function, let's say our function we were looking for was myfunc3, well, that would be 0, 1, 2, and we would just use that as our index into address of names, 0, 1, 2. That would give us an ordinal value of 3, and then we would eventually find our function pointer here. I don't think this diagram quite lines up, but you'll see it in the O&O editor as we're actually looking through the raw data to piece that all together. Okay, so again, keep in mind, address of functions, that's our actual function pointers. We'll resolve those. Address of names, that's the name of the exported function. Address of name ordinals is then a value that allows us to index into the address of functions. You will see from time to time functions that are exported by ordinal and not by name. And that just simply means that someone decided to skip the name and they knew the index or the ordinal value that the address of functions will eventually resolve to. So I guess it's a way of obfuscating it in a sense, but it's still, most of the tools that you'll be able to use to analyze this information will resolve that for you. Of course, we got a couple of tools here. PE Studio is always one. You can use the exports to look at what is the exported name, the library that it comes from, and let's see if we... Some of these here, you'll see that some of them are in fact forwarded, and you'll see that here as we get into the Hex Editor in just a minute, simply meaning that, for example, the acquire SRW lock shared, that function is actually, while it's exported from the library that we're looking at, it's actually imported from ntdll RTL interlock push list, and then whatever the rest of that name was, push list slist. Okay, so you will see that. For the most part, though, well, I shouldn't say for the most part, we're also going to look at functions where we're going to resolve that function pointer in the library that we're looking at. So virtual alloc, for example. I realize I jumped ahead just a tad. What DLL are we even looking at? Well, you can see up here kernel32.dll. What I ended up doing was just simply going to, in my VM here, Windows, so the local disk, Windows syswall64, and grab kernel32.dll. Copied that onto my desktop, and that's the DLL that we're going to be parsing, because you'll see that a lot of core functionality such as virtual alloc, create process, things that shell code and malware is going to use quite regularly is going to be in this library. Now, why syswall64? Because that's the 32-bit version of that library. You will also find kernel32 in the Windows directory, and no, I'm sorry, Windows System 32. And this then is the 64-bit version, right? Which would, if you grab the copy of this to follow along in this demonstration, things are going to be just a little bit different because it's the 64-bit version. So just so you're clear there. So again, grab those, drop them on the desktop, and then ask the tools to analyze them. DetectItEasy is another. You'll see here, just starting with the main screen, drop the DLL into the tool, and then you can go to export. This just provides sort of a different look into the same data. I like to have something like this or PE Studio open is that if I'm manually going through this with a Hex Editor just to sort of confirm the values or the data that I'm seeing, because that can be really helpful. Even though we're going to use O&O and we're going to use the template, there's some things, I guess you could say some magic that the template's doing the work for us, and we're going to parse the structure ourselves just for that better understanding. So you can look at tools, again, like DetectItEasy here, PE Studio, and it's going to show you the information so we can confirm that. So you'll see here's the ordinal value. These are the RVAs. We'll make sense of those in a minute. That's an RVA to the name, and then of course there's the names of the exported functions. Okay, I'm going to have windowbug open here. We'll get to this in just a moment so we can actually look at those function pointers. That just has a simple program. Any program will do as long as it loads kernel32, so you don't have to worry too much about that. And I think we're ready to just jump right into our binary with the Hex Editor. Okay, so one of the first things is to run the template, because when we look into the image NT headers and then the image optional header 32, we'll scroll down, and we've investigated these structures before, but we have the image data directory. This is an array that contains image data directory structures, and the first one is always going to be export, just like the second is always going to be the import. So we can expand that. We'll get the virtual address, and I'm going to try to avoid doing as many of the conversions as possible just for the sake of time. If you're not sure how to do that, we are going to do a couple, but the video previous with the imports, I go through that process quite a bit there. Instead, we're going to rely on O10 editor template to provide us with the file offset access. So this value 78C70, this is where the export directory structure is going to be located. The value is the virtual address. So in memory, 92C70 plus the image base, that's where that'd be located in memory, right? So we're just going to rely on that. Control G, that allows us to jump. We're going to do a lot of jumping around today, so might as well have some things handy to help with that. And that will jump us to this location. Now, really doesn't do us any good in this case to try to parse that manually. So here you can see 78C70. And this is our export directory for, in this case, the first DLL, which is kernel 32. Now, there are a number of different members here. The documentation that I referenced to you at the beginning of this video will have a better explanation of all of those, I think. I don't remember if I even bothered to look at them, because the only thing I usually care about is the number of functions, number of names, and then those 3 arrays that I had mentioned earlier. Sometimes this template can get just a little touchy. Okay, so here we can see our values for those 2 D words, number of names, number of functions, and then here we have address of functions, address of names, address of name ordinals. So I think it makes sense to start with the address of names, so we can look at and just get an idea of the names of the APIs that have been exported. So this has an offset of 7A5B4. And we'll jump to that location. And what you'll see now is this is a pointer to an array of RVAs. So each one of these array elements is going to be 4 bytes. They're going to be D-word values. And you can see that we have the value, remember the endianness, 96BCA. Okay, now I took a few notes before I started this, and what we have to find in order to convert those to be able to look at it on disk, because the template here just sort of does that magic for us. We have to know what section that's going to fall in. So you can go and look at the section entries and find the virtual address, figure out what section that is, and then we can use the virtual address base and the raw offset base in order to do these calculations. So this happens to fall into the RData section, which has a virtual address base of 80,000 hex, file offset value, of 66,000 hex. Okay, so what do we do with that? All right, we take the value 96B. I'll make sure we're in hex. Yep, 96B CA. Okay, right, which is this first element of that array. And then we subtract from it 80,000 hex. And then we add to that 66,000, which was the raw offset. Right, so 7C BCA is the value that we calculated, the actual offset in this particular file. So now we can go to our jump command, 7C BCA, and you'll find that that has navigated us to the beginning of this first entry, which is acquire SRW lock exclusive. Now, we also can see that the template has done that for us as well. Right? So now we can see all of these entries for this first library, kernel 32. That's how they're laid out right here. It's just going through each element of that array, calculating the file offset in order to identify the name. Now, once we have this first, okay, so if we step back and think, okay, if we're looking for a specific export, we would then iterate through this array one element at a time using a zero-based index. If this were the function we were looking for, well, then our counter would be at a value of 0. So now we would look at the address of name ordinals. Okay, this is at 7BED0. And this is an array of word values, so 2-byte values. So you can see there that that has a value of 3, and then 4, and then 5, and so on. So if we're at the first element, that means the ordinal value is 3. So now we use that value, and we would index into the address of functions. Okay, now we can go to our address of functions, which is at a file offset of 78C98. Okay, now remember that the ordinal that we just calculated or just obtained was an index of 3. So now we would look at this. This again is an array of 4-byte values. These are RVAs. So this would be 0, this would be 1, this would be 2, and then this would be 3. So 96BE2. So that value is added to the image base in order to resolve an actual function pointer. So that will then point to the function acquire SRW lock exclusive. We can sanity check ourselves here. We can look at, say, example, DetectItEasy, acquire SRW lock, and there's the RVA, 96BE2, right? Ordinal 4, but they're not using a 0-based index. They're using a 1-based index, I guess, for this listing here. So everything seems to match up. If we wanted to, let's see, look at that location though. Okay, if we wanted to actually look at that location, we could do that using windowbug. So I've already got, again, sort of an arbitrary executable. It's the import tables program from the video just prior to this. And here you can see kernel 32 is loaded at the address 75A5000. You can select kernel 32 to get information about that library. And in particular, let's say you weren't sure if it was 32-bit or 64-bit. Well, this tells us where this particular library was loaded from disk, and here it is. All right, C Windows syswall 64 kernel 32. And the reason is because the program that I'm using, I compiled to be 32-bit. So it's loading those 32-bit DLLs. Okay, so go back to here, and what we can look at then is I'm going to do a DA, dump ASCII, and you'll see why in just a moment. 75A5. So we need the base of our image plus the RVA that we just obtained, which was 96B E2. And when we look at that, we actually get a string ntdll.rtl acquire SRW lock exclusive. Right? This is one of those forwarded exports. So this is actually exporting functionality. Well, it's exporting functionality that it then simultaneously imports to another library. Right? But it all calculated. Okay, so what if we want to look for something maybe that's a little more common? At least when I'm looking at malware, you'll find virtual alloc a very common API. So we can go back to O&O, we can scroll down, looking at the value column here until we get to virtual alloc. Oh, sorry about that. So the template, because I had highlighted a field up here and then I scrolled with my mouse wheel, it moved to the next field and jumped me back. So I need to scroll with the scroll bar and then select this. All right. So virtual alloc is at an index of 1482, right? So if we were pretending like we were looping through this, then our counter for that loop would be at 1482. This is 0-based, which works out fine because the indexes that the arrays that we're gonna index are also all 0-based. Now you'll notice off to the side here that the comment, this is what this comment actually means, 1F3C0. It's already calculated for us via this template what this RVA is. So if we went to, let's just go back here and I'm going to scroll this down just a tad. Okay, there's virtual alloc, and we'll do a U command. So we'll disassemble at the address. There's the image base 75A50000 for kernel 32, and our offset here, according to O&O, is 1F3C0. And sure enough, there's virtual alloc. It's called virtual alloc stub here. I don't frankly know the history of why this stub, when this was added, it seems like about a Windows 10 thing. It's been on my list to look up and figure out as a kind of a trivial thing. But in any case, this is virtual alloc, and you'll see that it calls virtual alloc. But how did we get there? Well, 1482. So that would be our counter variable. If we wanted to, and let's do this. Let's load up, go back to our export directory structure. And the reason that I want to do that is so that I can get these offsets here handy, all right? We can also just use now windowbug. Okay, so let's look at the address of name ordinals. That's going to be at our image base plus the offset set 95ED0, as you see here. And again, keep in mind that these are word values or 2-byte values. So there it is. That kind of matches up with what we originally manually investigated. And we know our counter was 1482. I like to keep things all in hex. So we'll switch our calculator to decimal, base 10, 1482. That would be a hex 5CA. Now, one thing that you have to keep in mind is that is the index into that array. We now have to multiply by the size of the elements of the array. So this is an array of word values, 2-byte values, so we have to multiply that by 2 in order to get the correct address to index into the array. Okay, that gives us 5CB. 5CB then is the ordinal value into the address of functions. Okay, so let's do this. Let's look at the base of that array. Plus, and the address of functions is at an offset of 92C98. Right, there's that first value that we looked at. But now, similar to the previous, we have to add our offset. So we'll just scroll our debugger back up a tad, 5CB. And don't forget, that's the index into that array. Now we have to account for the size of each element. So we multiply by 4, and we get a value of 1F3C0, which hopefully looks familiar, because if we, in fact, I could probably just scroll back in my command history, 1F3C0, there's our call to virtual, or there's our pointer to virtual alloc, right? And if we look at DetectItEasy, scroll down here till we find virtual alloc. Oops, there we go. There's the RVA, 1F3C0. Okay, so this always takes me a little bit of time. I forget how to navigate all of these structures and do the necessary calculations. I don't typically do this type of manual calculation or investigating. Again, the reason why this is important is so that you can recognize it when you're reversing code, when you're looking at shell code, because that is a very common place for that to occur. Of course, if you're writing your own shell code, you're likely doing something like this in order to then, once your shell code is running in memory, it can actually resolve whatever functionality that it needs. So just to recap, we looked at the export table. We have the number of names, number of functions we can use as a counter. 3 important structures here: address of functions, address of names, address of name ordinals. Address of names is an array of names. If we get the index at which we found the name that we're looking for, that export, we can use that to index the address of name ordinals. Once we get that value from here, from the address of name ordinals, we can use that value as an index to get to index into the address of functions and get our function pointer. So hopefully this all made sense. If you have any questions, please feel free to leave comments and feedback, and look for those videos coming in the future where I show some practical examples of how the malware or any code in general can walk these export tables to dynamically resolve functions that it needs to call. So I hope to see you then.